Swayam Prabha. Digital India. Educated India.
Today we will be talking about improvement of bearing capacity in soft soils using geosynthetics. In the previous class we just understood how the bearing capacity of sands could be improved using Binkwith and D method, and then we also saw that the bearing capacity improvement is possible because the thing is that we try to calculate how much is the tension force required because of the friction between the soil and reinforcement. That is what we do there, and we also saw that the length of the reinforcement can be curtailed if you use anchorage concept. The thing is the concept of anchorage, in which there is a apart from frictional resistance, there is a bearing resistance that get mobilized. So, that frictional resistance plus bearing resistance can be very useful in the improvement of bearing resistance. So, we will see how it can be done in soft soils, because we know that soft soils are naturally poor, like the bearing capacities could be very low, particularly when you go to coastal areas. The soft soils are of quite you see them quite often, and you need to construct some structures, buildings and all that. And I just gave some brief introduction earlier to this method on how it can improve the bearing capacity. In fact, we know that the bearing capacity of the soft soil is given by CNC, like we call it C, and you have this term U, it is called undrained cohesion, okay. And then NC is a cohesion factor in bearing capacity equation. In fact, in bearing capacity equation we have three terms, NC, NQ, N gamma, which are nothing but the bearing capacity factors. And actually when we have this what we do is that when you are having soft soils, what we do is that the best method is to put on the soft soil some sort of sand, so that it improves bearing capacity. And if you are putting sand, you can always as well put reinforcement inside the sand. So, we have if you do that, there are some three mechanisms that we have, so that we can design the reinforced foundation considering these effects. One is called shear layer effect, the other one is confinement effect due to interaction between the sand and reinforcement in sand layer, and additional surcharge effects. This is what I meant, like you have a granular soil here, as this is a clay bed, and when you have a foundation here, what we do is that you in this the tendency for this material is to go like this, but then if there will be a passive resistance in the sand, okay, that is given by Kp gamma h. Instead of Ka gamma h, we know that is active pressure, but here it is a resistance is being given by the soil. So, we call it passive resistance, we say Kp gamma is h, okay. So, then you have this is called we call it shear layer effect. What we did was that we have introduced a shear layer of about h thickness, and it helps in bearing capacity improvement. So, whatever is that, like the load is not directly now coming onto the clay, it is coming onto the soft soil. In the same material, if you put a reinforcement here, see you have a reinforcement here, in fact you can calculate the total reinforcement force and you can even divide that, and anything can be done. And the advantage, if you put a reinforcement at the bottom, so what we are trying to do is that we try to provide a confinement effect, in the sense that when there is a load applied vertically, then there is some sort of resistance that get mobilized because of the friction between the soil and reinforcement. Because of the friction between the soil and reinforcement, there is a tension force Tr develops, okay. Then you have one vertical component of the tensional force that acts in the direction, in this direction, which will resist the bearing capacity. So, you have bearing capacity improvement because of this factor, like we call it shear layer effect, or we say TF1, okay. Then there is another term TF2, toe F2, you can say like shear resistance that gets mobilized at this plane. We have taken this is a plane, and then this is the shear resistance that gets mobilized, and now apart from these two, so this is called confinement effect, and it is actually the length of the reinforcement is L, and this is that effective length is LE. Okay. So, this is related to, say for example, it can be 2.5 or 3D and 3B or whatever. Okay. So, this leads to some sort of confinement effect, that is what it means. And when you have effects like this, like both these effects are now acting, they act as something like some surcharge effect actually, because in this reinforcement layer, you have these two combinations, you have what is called it is a surcharge effect we call it, and this decreases with distance exponentially, and there are some theoretical formulations for this, and we try to say that when S naught is Q S naught is this much, and then at a distance 1% of it there is the effective breadth, to some extent we can call it. Of course, lot of work has been done on these lines in Japan particularly, where you have all islands there, all are islands, and you have to construct some apartments there, and you have to see the soil is already there will be water actually, it is not even soil, you can't call it, it is highly liquid soil. So, you need to really put some sort of sand, put some sort of reinforcement, and then start constructing, allow it consolidate. We have to do many operations there, and finally you want to get a very good bearing capacity, then there is lot of effort required there. We will show you some of those results. And so, as I just mentioned, when you have a granular bed of thickness H of bulk density gamma s and friction angle phi s with reinforcement is provided over soft soil, the bearing capacity of the footing resting on this medium is increased, that we know, because it helps that there is some resistance. Frictional forces developed between the soil and reinforcement induce tensile strains in the reinforcement. The tensile strains developed provide the confining effect. This will introduce additional shear resistance along the vertical plane at the edge and exponentially decrease with distance away from the edge of the footing. So, even this additional shear resistance that you get, there is another component that you have, and so all the three things put together, like if you just say Q is the original bearing capacity plus delta Q R because of the reinforcement and surcharge effects, and also that sand layer effects, you can just say that these three deltas will add up to the add and then increase the bearing capacity. So, how do you find out? As I just mentioned, when you talk of shear layer effect, the shearing resistance that are developed along the vertical plane at the edge of the footing is given by, like as I just said, Kp gamma h. So, Kp gamma h square by 2 into tan phi s, because we need the vertical component of it, right. So, like this is that, and then the improvement due to shear layer effect is, suppose you say delta q into SL, it is nothing but there are two edges it is acting, 2 F1, 2 toe, it can be toe or whatever. Okay. So, by B. So, then I mean by this is the what per meter length we are calculating. So, what is actually the improvement is nothing but this divided by NC Cu. Okay. This will be the bearing capacity ratio. Okay. How much is the bearing capacity ratio? What we are trying to say is that it should be more than say 1 to 1.5, something like that. What is that number we are trying to get here, that we will see. Okay. Now, as I said, it is a confinement effect. The tensile force are generated in the reinforcement as a result of friction, and LE is the effective length, phi r is the friction angle between the reinforcement and soil, like it can be 2/3 phi, or like suppose you are using a geogrid or very good material, like if you have, normally we take as 2/3 phi, but if you have bearing resistance also added up, it can be even very high. It actually it varies from 0.6 to actually 1. It is a very good one means it is a very good rough material. The thing is that there is a no its frictional resistance is very high. Okay. Like in the case of soft materials, the frictional resistance could be much lower, like it can be 0.3 or 0.4 or something. So, 2/3 of tan phi is something 0.66, and in the case of geogrids it can be 0.8, and in some places it can be 0.5, 0.67. Okay. So, it could be higher also. So, what I want to say is that this term I already mentioned about the linear density ratio earlier, like you are trying to put the reinforcement across this material. So, you have some sort of spacing and length and all that. So, if it is a geotextile like a sheet, you call LDR is equal to 1, and for some metallics grids or geogrids it can be little less also. And there are two terms now. Frictional resistance is something, the friction angle between the reinforcement and granular fill, and LDR, and also the effective length. All these things are important, and based on this we should calculate the tensile force. How do you calculate the tensile force? It is like this. The reinforcement force is nothing but gamma S into H is the overburden acting into tan phi r into LE LDR, linear density. This is a term that we use. It is nothing but there is a weight of that material is acting, and into its friction angle of the friction angle between the soil and the reinforcement into LE, what is the length over which it is acting and all that. And normally it can be 2.5 to, it can be even 3B, 4B and all that. So, the TF2 developed at the edge of the footing due to the effect of the reinforcement leading to confinement is TF2 is TR tan phi s. Okay. So, yeah, you can get again that term. So, essentially once you get that TR and okay. So, essentially what you are doing is that I will just I think yeah, in the next slide it is there. This one, like this is what you are trying to find out, the TR and then multiply by the tan phi s, you get this vertical component. That is what we did here. TF2 is TR tan phi s, once you know that, and then once we know, so we know the improvement in bearing capacity due to confining effect. Okay. This is what you are getting here. Okay. So, there is a simple expression actually in given in one of the good papers, like all these two, both these two effects, shear layer effect and exponential effect will add up in this form, and then you actually you need to integrate, actually there is a distribution function for this and all that, and once you integrate and you want to get the number here, actually what you are trying to get, what is the value here is what you are trying to find out. It is there is a simple expression that we have, but it can be obtained with some simple calculations which are given in the literature, and you can take it for the time being that it is if you take it as exponential distribution, it is 0.84 times into whatever you have computed previously. Okay. So, based on these three things you are able to get all the three effects. So, let us see it in the case of a problem that we saw earlier. Design a continuous foundation of B equal to 1 meter that will carry a load of 480 tons, that needs to be constructed on the soft soil, and the under strength of the soil is 10 kPa. Okay. So, you can see that it is 480 tons, 480 kilonewtons is the load, and we know now the bearing capacity is only 51 kPa, it is 5.14 into Cu, like 10 kPa. So, this is a very low value. Now, you would like to improve it, and say let us take 2 meters as a thickness of the sand sand cushion you are going to have, and unit weight is 18 kg per meter cube, and that acts as a shear layer. What the shear layer is, that it absorbs all the shear strains. Okay. Now, you have this term Kp gamma squared by 2, actually okay, it should be 1 plus sin phi by 1 minus sin phi. Okay. This is it should be reverse, and you will get some number. Okay. So, you will calculate that it should be 1 plus sin phi by 1 minus Kp is 1 plus sin phi by 1 minus sin phi into gamma p into 8 into square and tan 30 and all that we have. Okay. It is 1 plus that we know that. So, you have a number which is something, okay, you got an effect of shear layer effect which is reasonably good, like what I meant was that you have a 62.35 kilonewtons, and you are trying to take on both sides, and so it is 124, and it is actually, if you see the bearing capacity ratio, it is actually original one was 51 kPa, and it is now you got a higher value. Now, let us take the case of reinforcement effect. Consider that a geotextile layer is laid at the interface of the clay and sand. The tensile forces are generated in the reinforcement is a result of as a result of friction between the granular soil and reinforcement. So, we take it as LR is the effective length and phi r is the frictional angle that we have seen, and we use the various terms like gamma s into h into tan phi r into Le. So, I am trying to use these terms like 18 tons, 18 ton per meter cube, 2 or whatever 18 kilometer per meter cube actually, okay, 18 kilometer per meter cube and 2 and tan 30 and 3 meters is the length of that, Le and LDR is 1, and you get some number. So, you again see that, and bearing capacity due to confinement effect is there 124.70, it is quite good. What I want to also draw to your attention is that now you have a 62 or 60 kilometer per meter is the length of the strength of the reinforcement actually. See, you can even put any material like as I said, what I did here is linear density ratio is 1 I have take 1 I have taken, but you can even put a wire mesh, steel wire mesh and with sand and all that. If you know how to calculate this material, it is all right, like you can even calculate per meter length. Say for example, if you are putting a wire mesh, you can calculate the area of cross section of the steel available, like say for example, if it is just a 3 mm wire at all that. So, in 1 meter length, what is the diameter of that you can calculate, and the tensile capacity of the steel, and you can calculate this number also. So, you will be able to even check whether this is actually this is a load that the tensile force generated because of the load, right. So, you can even check based on the what you have provided, what is the tensile resistance available. One can even get a factor of safety here. Okay. So, we can even 2 meters we have kept actually, 2 meters is one thing that we have kept. Okay, one can make it 4 meters, is it 3 meters is okay or 4 meters okay, one can make a parameter study, and if you want to make a very stiff reinforcement here, one can keep it here, all that things could be done. Okay. Now, the contribution to such an effect also one can make, as I just mentioned, one can calculate all these things. So, all these things put together it is about 458 kilo per. So, what I wanted was how much? 480. Do you remember? So, if you remember, the problem is 480 kilometer per meter, if you remember. So, we are able to get close to that number, and one can alter some of these numbers, like you can just go for a say for example, higher thickness, little higher thickness and all that, and see that it is 480 kilometer per meter. The requirement, if you remember, it is about 480 kilometer meter. So, we are close to that, right. So, definitely one can make some of the adjustments and get these numbers. Say for example, they have a number of design variables here, like here itself you can make something here, like lot of things could be made here. Thickness of the sand layer, first one is the thickness of the sand layer, and the second one is the effect of reinforcement, and this is another one. So, it is possible to use this technique and improve the bearing capacity considering all the 3 effects. That is what I would like to say. And in fact, I would like to draw your attention to ground reclamation methods in Japan. In fact, our country is big, and there is not, I mean, we have a lot of soft soil problems, but in particularly in Japan, no, they have a lot of soft soils. In fact, there is one institute called Institute of Lowland Technology. I know there is a saga. They develop lot of local techniques which are quite effective to construct in the case of soft soils. And in fact, they also discuss on the type of filling that you have to do and type of materials that you should do in the case of soft soils. This is a typical example, earth filling method. You are trying to go for bearing capacity improvement, it is nice. You can say for use soil reinforcement or surface soil stabilization. We have seen many techniques like using lime, using cement and all that one can use, like these are all the methods given here. And if you are using reinforcement, do you want a geotextile, you want a rope sheet, you want a geonet, you want a bamboo, and anything is possible. So, people have been using this, and okay, this is about bearing capacity improvement. And about filling, how do you spread the fill, like you got some sand. So, lightweight construction equipment small hydraulic fill pump, soil spreading barge. In fact, so they are all required. Okay. So they also have a similar design concept. I would like to just highlight to you. Say they do not have, suppose they do not have sand. Where do you get sand? So what you do is that you put a geomembrane, some reinforcement layer here, and we assume that it acts like a tension membrane. You know, you apply a load, and the load resistance is like, you know, any material can hold anything. Say you dump some material here, like if I just say this, like this is a sheet of paper, and if there is a building here, and it is called, there is a load applied and it deflects like this, and there is a tension component here, and the building will not further go. That is because the vertical component of the tension force will nullify the vertical load coming. So that is what is called, we call it tension membrane concept. On the same logic, we have here some load applied. Say for example, there is an embankment that you are trying to have, and you just have this sort of embankment, and you assume that there is a tension membrane which acts like this, and the tension membrane or the tension force has some sort of circle here, and there is an angle here theta and r, okay, and then the depth of the foundation is df. Okay. So just remember that, and we will just see how it helps. Now in the case of, so they have a simple approach similar to this, like the ultimate bearing capacity of the foundation is assumed to comprise of the four following components. One is the bearing capacity due to shear strength of the soil. We know that it is Q1 is CNC. Okay. Bearing capacity developed by the tensile forces generated both the ends of the geotextile reinforcement, it is Q2, which is nothing but because of the tension. The third one is the restraining effect of the geotextile on the ground deformation. Actually, there is another one that they have considered, it is called Q3, where the deformation, apart from improvement in bearing capacity, the deformation is also prevented, and restraining effect is there, and then the surcharge effect due to settlement and heave, that is another one. So they are all, you know, simple expressions are being used for that. It is Q1 is CNC, I told you, and Q2 is nothing but tension is mobilized 2T sin theta by B. B is the size of the footing and per meter length. Q3 is nothing but T into NQ by R, okay, gamma, sorry, NQ by this thing, so R actually, and I will show you. Then Q4 is gamma df, okay, this surcharge effect. So all put together are the ultimate bearing capacity. So now what is that you have introduced? A tension force is introduced, and the ultimate bearing capacity now is given by these all the three summation of all the three terms. Earlier it was only Q1, now because of this there is some increase, and one can calculate this increase based on this. Okay. So what they did was that design pressure should be equal to the sum of the pressures due to the fill and the equipment, like, you know, what is that, you know, you have constructed an embankment and there is a traffic load coming, and then the equipment. So the total load should be equal to QB plus QM, you know, due to backfill and the manufacturing thing. So the design pressure should be less than the ultimate bearing capacity in terms of the factor of safety. That is what we normally expect. Okay. So their own guidelines show that parameters for bearing capacity calculations, it is Japanese Society for Soil Mechanics and Foundation Engineering in Japan. You can say that df by h is something, if you see u is about, say for example 4, they just go to a depth of 0.5 or whatever, you know, they use a particular number. So for example 4 is 0.5, 0.6 here, in this case 4 it can be that angle of rotation theta, okay, what you saw earlier, it is about 40 degrees, and then r radius is something like here also about some range they have given. You can see it is a bigger range, but they have done some method, some analysis method, have that. I also want to highlight to you very important point here, that they have used some of this information and got the improvement in bearing capacity, and they are trying to put in the form of a chart, See, if depending on the underlying shear strength, this is here, you can see that the values are very low, like 0.1, 0.5, 1 kPa, it is very low actually. It is like it is less than more than liquid limit actually, it is 5 kPa here, 10 kPa here. So, actually beyond this, say beyond 1.5, about beyond 3, they have used geotextile here, and because it is very difficult to work in too watery deposits, like so they have used, in fact see the different earth filling methods also, dumped over water A, like you have all of these materials A, F, yeah, A4, F. Here see that these are all this strength is very low, 0.5 to 1, and then under water, when there is a water, so you have to dump and then put a geotextile, and the tensile strength requirement is about, you can see tensile strength of the geosynthetics about 80 to 100 kilonewton per meter. Okay. Then suppose you have this is all okay, A5 is dumped over water and a geogrid. Okay. A4 is also bamboo sheet, you can see they are all here. Okay. Then A2 is something that it is here. A2 is also a geonet. A1, A2, A3, they are all they have these materials. What about B? B is nothing but they placed and spread over land. Okay. So, there is another type, you have some material here B1, B3, B4, B3 and all that. Okay. Then even one can do pumping also. So, this is another type. So, what I want to say is that these are all practiced in Japan, I just want to highlight to you, and in fact, we have used it extensively in many of the bearing capacity problems. Many of the soft soils, they can have effective increase in bearing capacity using this method. Okay. So, what I would like to say is that use of geostatistics is very useful in bearing capacity problems to increase the bearing capacity and reduce settlements. The technique has been successfully implemented in many problematic areas, and the fact is that the research is continuing on material development. In fact, people have been working on different types of materials. They can be very stiff also, like the thing is that the soil is super soft soil, like, but then how to increase its bearing capacity? It is more almost like a liquid, but you want to have the structure there. So, people are looking at geogrid material testing development. Then design methodologies also, like of course, we saw two design methodologies actually in when you try to add up the Binkwith and Lee method for sands, and also just saw we saw in the case of soft soils two design methods. One is by considering the three failure mechanisms like shear layer effect, then confining effect and surcharge effect, and also the Japanese practice that we saw, and there is lot of scope for many more design approaches here, because one can do lot of modeling here using appropriate constitutive models and see if they are all right, and they can get lot of other insight also about other methods. So, then there could be construction influences. We saw that if you dewatering is an issue in some places. So, there is all construction issues, and some places you may you have to dump the water is there, but still you have to dump the soil on that, and there is lot of work being done on those lines, and any useful anything that can contribute to practice in this direction and improve the professional practice is going to be a boon in this area. A lot of work is being done, but still there is still a lot of scope, that is what I want to say. So, thank you, and now I will just take up the other one, which is very important again, which is the slope stability improvement. This slope stability improvement is something that is we need for every wherever you have a slope, you need to, if the factor of safety is less than 1, you have to improve it. There is no other solution here. And what I would be covering in this slope design is that why is it reinforced soil is required, or why is that reinforcement helpful in these slopes. Then we discuss some design methods, and one of the popular methods that I will discuss, and we will discuss what are the design parameters in that, and there are so many parameters there, we will see that, and what are the design values, how should you choose design values. Then what are the steps in design, and we will also see from an example. I told you earlier that the British code BS 8006 is something very standard in the case of reinforced soils and slopes. This is one of the earliest codes that came on this in this area, and because of which there is lot of advancement, people have been constructing reinforced earth walls, slopes and all that. The difference between a slope and wall is that the wall is vertical, whereas the slope has some inclination varying from 90 degrees to 35 degrees or 20 degrees angle of repose. The thing is, the slope, if the slope is having an angle of repose, then it is somewhat stable, but as the slope angle is increased and it approaches verticality, then the problem is that it is unstable. So, in fact, there are a number of methods of handling this, and BS 8006 indicates that the reinforcement of slopes is possible for a number of applications. One is reinforcement of a fill in a new construction, reinforcement of failed slopes, reinforcement of existing ground and cut slopes, reinforcement of an existing cut or a filled slope which is margin stable. Actually, we have done most of these applications, and I will show you some examples here. Like, say for example, reinforcement of a fill in a new construction, like say you are trying to go for construction, and if the bearing capacity of the bottom soil is not sufficient, you can increase the bearing capacity or slope stability. So, for example, what exactly you are doing is that by addition of this fill, the stability could be there is a possibility that there is a slip circle failure like this, right. So, you would like to avoid that, you place reinforcement like this, then construct. The other way is that some slopes can fail. Okay. So, one can really this is another one, reinforcement of a failed slope, one can do like this, this also they can do, and filling, the thing is, some of these things are quite simple to do, and reinforcement to improve the existing structures, like suddenly we realize that the slope is not stable, and one can do that. Okay. So, there are many applications of this. How do you do this? In fact, in the design, we know the classical slip surface method. If this is the height of the embankment, we know that these are driving forces. So, the resisting forces are from the slip circle, length of the slip surface we know, and there is some surcharge and all these things are acting. These are some notations that we know, standard notations. What we know is that based on the slip circle analysis, like how do you do the slip circle analysis? You may remember that you have to take say this is a slope, you have to divide that into a number of slices, and then for each slice you should see that if the conditions of horizontal sigma v, sigma h and sigma m are satisfied, like the resisting forces are from the shear resistance of the soil, and the driving forces are from the weight, or it can be even from an earthquake, it can be even from seepage. So, all these things one should consider and then calculate the factor of safety. In fact, you have so many programs nowadays to calculate slope stability, like it gives in terms of the factor of safety, right. And if you do finite element analysis, yes, it is also again possible, and the slope stability can be computed. Even you can also relate it to deformation in if you are using flak, say for example flak if you are using, one can calculate the factor of safety and also the deformation, because they use strength reduction technique for factor of safety evaluation, where the C plus sigma tan phi, the strength parameters are successively reduced till the slope achieves a condition of failure. Okay. So, once you know that this stability is not there, what we do is that we put some sort of reinforcement here. So, like we again this can, it is a matter of design here, like you have some sort of reinforcement at some spacing and some length and all that, and calculate again the factor of safety. What happens is that if this is a slip circle, this is a slip surface and this is a slip surface, and you have a reinforcement here, the 3 reinforcement layers, you try to, as I just explained the principle of reinforced soil earlier, that the if you just resolve this tensile forces in the reinforcement, it adds to it reduces the destabilizing forces, it increases the resisting forces. That is what we saw, that equation we know what is the extra shear resistance because of the reinforcement and its location. Even we have seen what is the optimum angle and all that, right. So, based on that we know that if you put some sort of reinforcement of adequate length, because the moment you put the reinforcement it should not come out also. So, we have to provide adequate length, and that is what we do. So, there are many methods to understand this problem. We call them as limit equilibrium methods, and what we do here is that we assume a suitable failure mechanism, like if we assume that it fails in the form of a circle, like a beautiful slip circle, then we also assume that it can be a logarithmic spiral, it can be a wedge, instead of a single wedge it can be a 2-part wedge. So, there are number of assumptions that one can make and calculate. The assumption is essentially to know that, like as I just mentioned the previous thing, that you have to make an assumption about the failure surface. Once you know the assumptions as I just mentioned, and if you put some sort of reinforcement, you can calculate what is the tensile force required to have a factor of safety of 1.5, is it not? You can always put some sort of reinforcement elements like this, and then you write there are so many slope stability programs nowadays in internet and even commercial software, and you can just calculate what is now factor of safety without reinforcement, and with reinforcement what is that, and how much, say for example I want a factor of safety of 1.5, and what should be the length of the reinforcement and the tensile force, all can be made, and you have a lot of opportunities there. So, these methods are essentially dependent on the failure mechanisms, and one more thing one should be very clear, that the mechanisms are something that we have to assume here, like then only it is possible to calculate. Okay. Now, there is another one, what we try to do. So, there are many people who worked on these lines, like the calculation of earth pressure coefficients using limit equilibrium methods is a classical problem. In fact, if you want to calculate the earth pressure Kp or Ka, how do you evaluate it? You have to assume some make an assumption about the failure surface, whether it can be a wedge, whether it can be a circle, whether it can be a, you can calculate. Once you know the earth pressure rest, one can define and then calculate what should be the value corresponding to a certain angle like phi, or certain properties like we know that, say for example the why the earth pressure, how much of earth pressure is coming and how much of earth pressure is to be designed, which would be the design coefficient for the earth reinforcement, one can find out here. Okay. So, there are a couple of people who worked on these lines. In fact, we also did some work on calculation of earth pressure coefficients for seismic different for seismic conditions and all that. So, when you are trying to design the reinforced soil slope, normally you have some parameters. One is, what is the slope angle? So, what is the angle that you need? So, is it beta? Beta is a slope angle. It can be even vertical also, but say what is the 70 degree slope I want, I can say that. So, then large strain friction angle, in fact as I just mentioned, friction angle of the backfill, this is a backfill. Okay. Then pore pressure coefficient is something that I should introduce you now, in the sense that we know the uniform soil is there, and pore pressure coefficient is nothing but U1 by gamma Z1, U2 by gamma Z2. Like, what is the ratio of pore pressure to its overburden pressure is something that we say, U1 by gamma Z1 and U2, we just say they are all constant. Maybe suppose you say that it is 1 meter, you know, pore pressure raise, you know, how do you measure the pore pressures? You have to measure using some sort of equipment. Actually the pore pressure is nothing but it is in terms of the weight of the water column heights. Suppose you say that it is 1 meter height into the unit weight of water is, we know, 1 divided by gamma Z1, you know, we know roughly it could be gamma is Z is same, you know, Z is same, and then at the same thing it can be half. Okay. If the pore pressure is fully mobilized, say pore pressure, how do you measure? It is nothing but the Z1 into gamma W. Gamma W is the weight of water, right. Okay. So, Z1 gets cancelled and it is just the ratio of unit weights of this water as well as the soil. Okay. So, it could be roughly about 0.5, and so that is called pore pressure coefficient. Then if you are placing a reinforcement like this, okay, the requirement is that you need to have a bond coefficient. See, the thing is, I said the reinforcement should not fail by tension or by bonding. So, if it bond coefficient is, what is the bond coefficient? Like, you know, you say that the bonding is provided because of the friction and the geogrids. Suppose you are using geogrids, that bond coefficient you should calculate. Okay. In fact, if you remember the example of the bearing capacity problem, we calculated the bond coefficient there. We took sigma b by sigma n, if you remember, and we have an expression also which is in terms of the tan phi of the soil and the failure mechanism, and we did that. So, bond coefficient one can get based on those assumptions and calculations, and direct sliding coefficient is nothing but tan delta, or tan delta, which is nothing but which is nothing but 2/3 of tan phi. Okay. So, that is one thing. So, all put together there are some expressions. In fact, I advise you to go to library and read the book by Jival. You know, it is a very good book on reinforced soils, please read it, and I am just essentially following that book for this particular lecture. Then, okay, you know, these are all some soil properties and all that. You know, how do you like see the moment you want to design the slope, you need soil properties. What type of soil is there? So, design values for the shouldering distance is nothing but phi dash d is nothing but phi dash cs. Which value of phi I should take? Is it a peak value? Is it a large strain value? So, here we are taking a critical state large strain value actually, and experiments have shown that this phi cs is in the range of 30 to 35 degrees for granular soils, and low plasticless maybe 20 to 25 degrees. Okay. Then maximum expected unit weight is nothing but gamma d, we know that, right. Then suitable pore pressure coefficient. For example, we know that the soil is going to be dry, there is a good drainage, so water may not stand. Okay. So, pore pressure in the case of a dry slope is 0, like as I just mentioned, pore pressure is what, u by gamma z. When u is 0, pore pressure is 0, or when there is a water head or there is some partial saturation, there could be some water head, and you can say that pore pressure coefficient is say maybe 0.3, 0.1 or 0.5, maximum is 0.5. Okay. But as I just said, it is a ratio of the unit weight of water to the unit weight of the backfill. So, if the unit weight of the backfill is going to be less, then you have to make it make appropriate corrections. Now, how do you choose the reinforcement? As I just mentioned, we are using geogrids and geotextiles and even geocomposites, I just mentioned in Vizag Kanakadurga temple, they have used geocomposite. Okay. And how do you select the geosynthetic material? That is very important. We know that why do we choose reinforcement? Reinforcement we know we need because it develops some force in the reinforcement. Okay. There is some force that gets mobilized because of the reinforcement, that friction between the soil and reinforcement. So, the reinforcement force should act till its design life is complete. Say for example, if the design life is Td, right. So, that design force should be, what in this figure what it shows is that you have some allowable force and you have what is you get from the manufacturing side. Say for example, a particular material you can choose and you can get that what is allowable you can calculate from calculations the way. So, the what is in this material should be always more than what is actually required or what is allowable, there is some minimum value here. So, actually FD is nothing, there are damage factors, F is environmental factor, and we always see that these materials are always here such that the allowable reinforcement force is there all the time. Say for example, if you are trying to construct a slope, the slope should be stable for 50 years. So, when it is 50 years, you may have a reinforcement force like this, which is in the beginning, that it may come down with time. It is about, say for example, 50 years. Okay. So, that force should be more than what is required here, that is very important. And as I just mentioned, these are all manufactured materials in the some standard conditions, they will have some damage, they have some environmental factors and all that. You have to make all those corrections and see that this is all right. So, that is what I want to say. And the allowable force P allowable in the reinforcement must be selected to allow for conditions in the ground at the end of the design life and the design temperature. Actually, many of the geosynthetic materials are plastic, as I said, they are all polyethylene polymers essentially, and they have they respond to temperatures and biological conditions also sometimes. So, one should be very careful, and so we have some partial factors of safety here. Mechanical damage 1.1, maximum is 1.6, environmental factors 1.1, and if you have not much data, it is 1.3, and if you are trying to extrapolate to 1 log cycle, it is this thing. Yeah, see, you have reference properties and this is 1 log cycle. So, for example, this is log 1, this is log 10, this is log 100. So, this is 1 log cycle, this second one is second log cycle. So, if you have that, the correction factors are 1.5, 2.2. So, you apply all these correction factors to that, and also a overall factor again, one more you can, if depending on the importance of the structure, one can make, these are all material partial factors, and the overall factor of safety is also given, and this is based on the company's literature. Okay. Now, once we know that we know about backfill soil, we know about the reinforcement to some extent. I just gave some information about this. What is the difference between bond and sliding? Okay. So, as I just mentioned, sigma n is the normal stress, tau is the shear stress. So, tau by normal stress is nothing but Fb into tan phi d. Okay. So, Fb is nothing but the bond coefficient, okay. And in the case of geogrid, you can imagine that it is not easy to work, it is not easy to pull out because of the grids and all that, and there is some pressure. So, all that. So, this is one thing, that is bond resistance is going to be higher, and it is a function of normal stress. And you also have what is called direct sliding. You can see that the nice slip circle is formed and then it is getting slid on the previous thing, right. So, you are able to understand what is these two. Okay. So, the direct sliding coefficient is nothing but it is a measure of the shear resistance of the soil, and it is not normally given in terms of the FDS stand for preferential sliding across the surface of the reinforcement layer. The bond coefficient is the due to bond through shear on the plane reinforcement surface as well as bearing, and depends on the proportion of the grid and the shear resistance of the soil. Like as I just mentioned, now if you have a geogrid, when the shear takes place, there is a contact between the soil to soil and also soil to geogrid and also bearing resistance. There are a couple of things there because of which the bond coefficient will be higher. So, how do you do this design if you have a reinforcement? We see that if I remember, do you remember that there is some lateral force coming up, and if you put a reinforcement that we have a maximum, see we have to have what is called the basis of design is the calculation of distribution of maximum required stress to be supplied by the reinforcement for equilibrium. In fact, if you introduce the reinforcement, it will introduce some stress into inward stress. The thing is that it is like this, there is an outward stress, but then if you put a reinforcement, there is an inward shear stress, and so that is because of the tension between the soil and reinforcement, and so the calculation of the maximum required stress to be supplied by reinforcement for equilibrium means the material should be stable, the slope should be stable, and that depends on the required stress or the maximum stress. So, a suitable provision of reinforcement can then be made with sufficient strength and spacing, so that minimum available stress from reinforcement exceeds the maximum required stress. What is that we are looking at? Actually, whatever is that there is some stress that is coming, and if the stress supplied by the reinforcement is much higher than the stress that is required, then we are safe at all levels. Like say for example, we know that K naught into gamma h will be the earth pressure into SV into SH. Say for example, SV is the vertical spacing and SH is the horizontal spacing. So, K naught into SV into SH will be the horizontal force, and if you put a reinforcement, that is nothing but the force mobilized in the reinforcement. So, we try to see that the reinforcement has sufficient length and spacing, and it is always safe, such that the a suitable provision of reinforcement can be made with sufficient strength and spacing to see that available minimum stress, whatever is that you have provided from reinforcement is always more than the maximum required stress for equilibrium in soils at every depth. That is what is the principle here. And to do that, in fact, how do you calculate the maximum required force? See, the thing is, if the wall is vertical, how do you calculate the maximum vertical force? It is Ka into gamma h square by 2, right, is it not? Then if there is some inclination, we say that we also allow, as the wall slightly comes down, then there is a reduction in the earth pressure, we say that Ka will come down, right. So, earth pressure, and then when they finally it approaches the angle of repose, the earth pressure is 0. So, that is what we are trying to do here, like earth pressures are calculated. In fact, this is a chart, design chart given by Jewell, and you can see that for different friction angles phi d is here and K required is this, and slope angles. So, for example, slope angle is 90, and if the friction angle is 20 degrees, the K required is higher, right, like say 1 minus sin phi in the case of a vertical wall. How much is that? Say for example, if you take friction angle as 30, right, 1 minus sin phi one can calculate, you will get some 0.33, right. So, this is the standard one, and the advantage of this plot is that it gives you the what is the required force. So, this is to be supplied by the reinforcement. Okay. So, this is one thing, and actually once you get the required reinforcement force from, say for example, what you are going to do is here in this chart is that if I know the sand material that you are using for the backfill, say for example 30 degrees, and if the slope angle is say 70 degrees, it will be the 0.2 will be the required air pressure coefficient. Okay. So, 30 degrees is here and then 70 degrees is here. So, it is about 0.2. Okay. This you should remember, and this type of charts are prepared for pore pressure equal to 0.25 and 0.5 and all that. That is a simple matter that he prepared. Once we know that this much of force is required from the reinforcement to keep the stable slope, I mean slope stable, whatever is the angle, then the length is also important, because there are two things that we have here. One is the length required for stability. Minimum length of the minimum length, see there is some, you place reinforcement in the slope, at the earth pressure at the top is less, at the bottom it is higher, and the minimum length at the top is the crest is that required for overall stability. Actually there is another, we have different considerations. This is from tension consideration, and the other one is overall stability considerations and sliding considerations. See, in anything, like see, the moment you construct something, it should not lead to failure, like it should not lead to failure by first thing is the reinforcement force should have adequate internal resistance, should give that, and also it should not fail by overall considerations, and also it should have sliding also, we will see that. So, the minimum length at the crest of the slope is that required for overall stability. The minimum length at the base of the slope is the greater of the required for overall stability and to prevent direct sliding. In fact, we calculate the length of the reinforcements at the bottom by sliding considerations and also overall stability considerations, and whichever is higher you take actually, okay, greater of the required will take it. And when where the length, say for example, if the length of the reinforcement, as I said, if you remember that at the top the earth pressure is less, but then the pull out resistance, but you can't provide a short length because the overburden is less and pull out resistance has to be more. So, length is little more. So, length is little longer, whereas at the bottom the earth pressure is somewhat higher, and though the overburden is higher, that consideration the length could be little the tension force governs the design here, whereas pull out resistance governs the length of the reinforcement at the top. So, what we do is, as a via media, we try in for some small heights, the reinforcement will be of constant length, like if 7 meters or 10 meters is the height of the ball, we say 0.7 times is the length of the reinforcement. Okay. Then where the reinforcement of constant is used, they select the greatest strength required to satisfy the required at the base of the slope. Okay. We normally provide, I will show you that, and when direct sliding governs the required reinforcement length at the base of slope, it is permissible to reduce the length uniformly from LDS at the base of the slope to L overall at the crest of the slope. This is a diagram that we will see, we will discuss this much more after the break. In fact, the length of the reinforcement is for different angles and all that one can get what should be the length, and there is a minimum length required from sliding considerations also. So, for any slope one can get this. Okay. I will stop at this stage.